Okay, hello everybody. We're going to compute the Furness array frame, or the TNB frame, for this curve, the twisted cubic curve, at the point or time t equals 1. Okay? So if we have some curve, let's call this gamma. It takes time into space, and so it's our movement as we move around space. And so let's say we're moving around, and then at this time, maybe let's say right there, we're at gamma of 1, at time equals 1, sort of gamma evaluated. So we're evaluating the map at t equals 1. Gives us a point in R3. And at that point, there's going to be sort of our unit tangent vector, so this has length 1 vector. Then there's going to be the unit, so a unit normal vector, and it's at 90-degree angle with respect to the unit tangent. And then there's the unit binormal vector, so this is again a unit vector. And it has 9 degrees with respect to the tangent and 90 degrees with respect to the unit normal. So this gives us sort of a frame, 3 dimensions of space according to us, the world as we see it, as we're flying through space at the moment time equals t equals 1. Okay, so first I'm just going to write down that t is the unit tangent, and it's equal to normalize the vector gamma dot at 1. So just normalize the velocity. Okay. N is called the unit normal, and it's equal to normalize, so make into a unit vector, what vector? The acceleration, and I'm just going to leave off the evaluate at 1, just to make it easier to write. I'll even get rid of that one. So it's the acceleration minus its component in the velocity direction. So that's because we want the unit, the acceleration might be pointing somewhat in the tangential and somewhat in the normal, and we want to remove the tangential component. So if the acceleration was here, we want to remove it so that it's orthogonal or 90 degrees with respect to the unit tangent. Okay, so we know how to do that. Gamma dot dot, gamma dot, gamma dot, gamma dot. So that's the formula for projecting. Okay, and so we just normalize this vector. Okay, and then what's b? B is the unit, it's again a unit vector binormal, and it's going to be the cross product of t with n. Or, we could also write this as t cross n. And because t and n are unit vectors, so will the unit binormal be. Okay, so now we just need to calculate. So first I'll just redraw my curve. T maps to t squared, t to the third. And so what's gamma of 1? Well, I just plug in t equals 1, and I get that point. So that's like here. It's the point gamma of 1. It's where we are. Gamma dot is the velocity. It sends t to 1, 2t, 3t squared. Okay, and the velocity at time 1 means we plug in t equals 1, and we get that vector. Pause this if you want to take your time and just make sure you follow what I'm doing. Gamma dot, or double dot, is the acceleration, and now we take the derivative one more time, and we plug in at t equals 1. Okay. And so we'll also need these dot products, so why don't I just compute them right away. Double dot with dot will give this dot product, so what do I get? Okay, and then I have to divide that up here, I have to divide that by dot, dot with dot. Okay, that's quite silly. It's the velocity dot product with itself. And so that will give another number from this vector dotted with itself. Okay. So I can simplify this. This is 22 over 14, which is 11 over 7. Okay, so I'm basically ready. Oh, one more thing. I have to normalize. Oh no, I already did that, so there it is. So then what's the length of gamma dot of 1? Well, that's the square root of this number, square root of 14. Okay, so that's how I'm going to normalize. And so, okay, let me just plug in. Normalize gamma dot. Well, I see down here that gamma dot at 1 is 1, 2, 3. And I need to normalize, so I have to divide by its length. Okay. This is t. Okay, so now for n, what do I have to do? I need to normalize. So I don't want to forget to do that, so I'll write the word normalize. And now what's gamma double dot minus this stuff? Gamma double dot is 0 to 6 minus, well, what's this stuff? It's 11 sevenths. I have to remove 11 sevenths of the velocity vector, which I know is 1, 2, 3. Okay. And so now I'm basically done. I mean, I know the unit tangent. I basically know that, after I subtract these vectors, then I divide by the length, and I've got the unit normal. And then finally, if I take their cross product, I get the unit binormal. So the rest of this problem is tedious calculation. So let's continue with tedious calculation. But now we know what's happening. The conceptual part of the problem is done. We were getting the t and b, and we thought about how to get them. We normalized the velocity, and then we normalized the acceleration minus its component in the velocity, and then we take their cross product to get that third orthogonal vector. That's it. How did we do that? We took the original curve and its derivative and its second derivative. We plugged in at t equals 1, and then we just computed these dot products, essentially projecting the acceleration normal to the velocity to create the unit normal. Okay, so let's continue. So over here, I'm going to make this calculation. Okay, so to subtract fractions, you need to take a common denominator. So what I'm going to do is say 0 over 7, 14 over 7, 42 over 7, 11 over 7, 22 over 7, 33 over 7. Do you see what I did? Pause. Okay, now I just subtract. Okay, so 0 minus 11 is minus 11. 14 minus 22 is minus 8. 42 minus 33 is 9. Okay, and if I want, I can just remove this. Okay, so I need to normalize this. So I need to normalize this. Okay, well, I can just get rid of the 1/7 because if I normalize the vector, it'll have length 1. So I'm just going to multiply this whole vector by 7 and then normalize that. And it's just sort of a simpler thing to do. So essentially, what I have is 1 over the square root of 121 plus 64 plus 81 oops, 1 over that times, oops. Okay, so essentially I was able to ignore the 1/7 because I'm changing the length of this vector anyway, so I might as well multiply this vector by 7 so it has nice integers, and then divide by its length. And so I can do this, so 121 plus 64 is what? 185 plus 81, 266. Is that okay? Okay. So I believe the unit normal is 1 over the square root of 266 times the vector with these integer components. Okay? So now I have the unit tangent, and I have the unit normal. The unit binormal is equal to the cross product of t with n. So what is this? This is equal to the determinant of the matrix who has E1, I hat, I could put I hat, J hat, K hat in this matrix. Or I actually prefer to put the unit vectors E1, E2, E3. But this is just symbols, it's just naming those vectors, so it's okay. And now t goes here. Just remember t is up here, 1 over square root of 14. Now the determinant is linear in each row, so I'm going to tell you that I can pull the 1 over square root of 14 out and put the 1, 2, 3 there. Same for n. Now n has to go here, but the determinant is linear in the rows, so I can pull out the scalar and put negative 11, negative 8, 9. And if, of course, in a computer, I would have just typed this, and it would have done this all for me. But we can do it. Now the determinant is E1 times 2 times 9 minus negative 24 plus E2 times minus 33 minus 9 plus E3 times negative 8 minus negative 22. Okay, so that just means I have, well, what's 18 plus 24? 30, 42 in the first slot. What's this? Negative something. Negative 24 in the second slot. And negative 14 in the third slot. And that's all divided by the square root of 14 times 266. Okay, and that's B. That was a lot of calculation. To be honest, you would have a computer do this, but I just wanted to show you that finding this TNB frame can be deceptively difficult for even the simplest curves like this twisted cubic curve. Finding the derivatives was easy, but when you're projecting and things, the actual calculations can get quite involved. The cross product is sort of this mysterious thing that only works in 3 dimensions, but we can calculate it, and more importantly, a computer can calculate it. So at the end of showing you how to do that, here's what I'll say. The answer that you need to give me is the unit tangent, and then this piece, I don't even mind if you leave this subtraction of fractions undone. But if you have this, I mean, this says exactly what the answer is. You've computed the answer, except you just haven't done the subtractions or the normalizing. But if you wrote this word, then you know that you need to do that. And then finally, the cross product is just something that that we just have a computer do. It's a determinant. It's an unpleasant calculation. We should, so in other words, these 3 purple boxes are sort of your final answer. I require this kind of work for sure in order to get this box. And this kind of thing is definitely required, so I know that you understand what's happening. The picture is useful. This didn't ask for the picture, but I would do the picture just so you remember what things are. And all of this calculation is not required if you leave it like this. Okay.